Yeah, thanks. So Ryan said he was going to give a whiteboard talk, and so he inspired me, and so I'm just kind of bored with slides. And so I was just going to write on the board and see how it goes. Also, I'm super jet lagged because I stupidly took United and was delayed for 6 hours, and then my bag took an hour to come out of the thing. And I got in at 3 in the morning Pacific, and I usually wake up about 4:30 Eastern, and so it's kind of threw me off a bit. Okay, so I want to scale up Bayesian inference. So what the hell does that mean? So usually, you're doing Bayesian inference, and so you have some sort of likelihood function of y given theta. Okay, so this is your data, and this is your kind of parameter, or unknowns. Okay, and so what usually people do, I think, when data are really big, high dimensional, or the sample size is large, you tend to, in modern days, kind of just focus on optimization. And so most of the literature is based on kind of getting a good estimate of theta hat. And maybe theta is enormously high dimensional, and so it could be very, very big, huge matrix or tensor or function. And we're trying to efficiently get theta hat, even though the sample size is huge and the dimension is huge. But in the applications I care about, we really super care about uncertainty quantification because we want to do scientific inferences. And so we run a study, and we have limited number of patients, and the variables we collect on the patients and the unknown things we care about in doing scientific inferences are really high dimensional. And so you can't really do this kind of deep learning thing or something like that, or just do point optimization, because uncertainty is everything. Okay, there's a huge amount of uncertainty, and you have to quantify it well, or your scientific inferences are going to be totally messed up. The literature will be full of false positives, false negatives, and errors. Okay, we don't care about just a black box for doing pattern classification. We care about scientific inferences. So maybe this is data on brain structure from different humans, and you want to know how brain structure is related to phenotypes like depression or autism. Okay, or maybe these are genomic data, and these thetas over here are parameters characterizing which genes are related to some particular disease of interest. Okay, and so these are really high dimensional, but the sample size might not be that huge.
And you said deep learning is no good because what?
Yeah, so it's funny because I think that like machine learning has been taken over by deep learning, partly because everyone in machine learning, mostly everyone, is focused on these kind of industry problems. These industry type problems where you have huge sample sizes, huge amounts of labeled data. So if you have a small sample size, not much training data, not many labeled data, and the dimension is big, and you don't have some very, very intricate, carefully structured data like an image, but you have data which has an unknown structure and is high dimensional, then these deep learning methods are not designed for that type of setting. And I think that it's been really a shame that everyone has kind of shifted their focus to the setting where you're almost always industry applications and not so much science, like biomedical science or science beyond, these kind of cases where you're trying to identify what's in an image or do audio classification or industry type problems. And you can disagree with that if you want, but I really haven't. It's been overhyped, the deep learning, in the setting of scientific inferences, where we almost always, in the scientific applications I have, you have limited data. The data tend to be high dimensional, and we have a lot of uncertainty, and we don't want a black box for prediction. We want to understand the structure, okay? And so I'd like to have a call for machine learning people in general to work on these problems more. If we do some sort of sparse structure learning, and you get a point estimate of that structure, that's just about useless because that structure might not be representing the true science, and then you're like reading tea leaves and propagating false positives in the literature, which is not good. Yeah? And so that's one reason that I, not philosophically necessarily, but just as a practical matter, I tend to focus on Bayesian type of approaches because it provides a convenient paradigm for characterizing uncertainties. Okay? Not perfect, there's problems, and it would be wonderful for people to be thinking, kind of stepping back and thinking philosophically about how to solve some of these problems, like robustness to the model and things like that. Okay, but anyway, so talking about a little bit about the kind of what can we do? Well, we're going to have a likelihood, parameters, parameterizing the likelihood function, and the likelihood of the data if we're doing a Bayesian approach. We're also going to have a prior, pi of theta, some probability distribution on our unknown parameters. Okay. And then from that, you're going to get a posterior distribution. Okay, and so that's pi of theta. L of y given theta divided by what's a normalizing constant, which is the marginal likelihood. Okay. Call this L of y. And so usually, so this guy is kind of characterizing uncertainty. And so you could think, well, here's the parameter space, theta. And so this is a probability distribution over this parameter space. Those parameters could be which subset of the variables are important in predicting depression from brain structure. It could be other things as well, okay? And so we have some generic posterior distribution. And so we can, in general, do inferences this way, quantifying uncertainty. And what happens in high-dimensional problems is a couple of things. So the one thing is that if this parameter space is large, then this integral is very high-dimensional. Okay, and this can be very difficult to analytically approximate. And so Dave Bly has done amazing things with variational methods, trying to get some type of approximation to this posterior distribution based on some sort of variational approximations. But often we don't know how well those are going to do. They might do well in machine learning contexts or industry applications, perhaps not so well in scientific applications where we really care about quantifying uncertainty accurately. Okay. And so if we have this posterior distribution that's going to be high dimensional, we have this difficult integral. It's usually not in closed analytic form. And we might also have difficulty evaluating it because it's computationally expensive. Okay? And so what do people usually do in this setting? The kind of tools that have been around for a while are Markov chain Monte Carlo, okay? MCMC or Markov chain Monte Carlo. And so the game in Markov chain Monte Carlo, which is the introduction of these methods, is what really caused Bayesian methods to kind of take off in general, is that we can bypass having to calculate this integral in the denominator, and we can define some iterative sampling algorithm where the samples converge to a stationary distribution, which is this joint posterior distribution. And then based on those samples, we can do our inferences. Okay? And so the game is we define some sort of Markov chain on theta t's. We iteratively sample these theta t's, and they're going to converge to a stationary distribution, which is this joint posterior distribution. Okay? And it's kind of revolutionized use of Bayesian methods, these MCMC algorithms. And there's a whole set of different algorithms. Ryan Adams is one of like the really kind of guru in discovering new types of algorithms for difficult problems like Gaussian processes and nonparametrics. Okay, and so what do we do though? So if we're in a small dimensional problem, if theta is not that high dimensional, then this is very well developed, very general MCMC algorithms. But there's some problems that arise in big and high dimensional data. So in big and high dimensional data, we have some problems, okay? So we might have, computational bottlenecks per iteration. Okay? So so we're going to define a Markov transition kernel. It might be a Gibbs sampler. You would sample from each of the full conditional distributions. And so if you had a parameter vector theta 1 through theta p, you might sample theta 1 given the other thetas fixed from their full conditional distribution and then cycle through. And that would be defining your Markov transition kernel in the Markov chain, and then you keep doing that. Okay? Or in general, Metropolis Hastings algorithms, you would instead define a proposal and accept or reject. Whenever you're doing that, you in general need to evaluate the likelihood function. You might need to calculate gradients. You often have to invert matrices that might be have computational bottlenecks that's like order n cubed in the sample size. And so you're going to get, per iteration slowdowns. Okay. You're also going to get problems with what's called mixing rate problems. So what we want to do in Markov chain Monte Carlo is we're sampling these theta t's, and so we'd like to sample the theta t's in a way so that they converge really quickly to close to the stationary distribution, which is the posterior distribution, and we'd like them to mix really well. And so in an ideal world, we could even generate independent samples from the posterior distribution, but in reality, they're going to be autocorrelated. And so if they're very autocorrelated, that would mean that the Markov chain is slow mixing, and you're going to have to collect a lot of samples, maybe 10,000 samples instead of 100 samples to get the same Monte Carlo error and some statistical estimator we care about. So one of those might be, for example, a confidence interval or credible interval characterizing uncertainty in one of the parameters, theta 1. Or you can do it really for any functional of the parameters. You can calculate, say, point estimate, a posterior mean, and a 95% interval. Okay, so we have these two bottlenecks. And so what we'd like to do, what we're doing we have a NSF Foundation's a big data proposal right now, and I've been working with the group of postdocs and students and a professor in the math department on kind of trying to study the properties of MCMC algorithms and develop new algorithms to solve these bottlenecks, okay? And so, because I think that we can actually scale MCMC up to really quite big problems and be competitive with things like variational algorithms, particularly using parallel processing, okay? And so what are the games that we could play? There's going to be three things I'm going to talk about. The first one is embarrassingly parallel MCMC. So can we, MCMC seems to be intrinsically a serial algorithm. We iteratively sample from this transition kernel, the theta t's, the whole theta t vector, and we conceptually would have to hold all the data in memory on one machine or processor to do these kind of operations. And so that would be a problem, but there's now this kind of increasing class of embarrassingly parallel MCMC algorithms, which we've contributed quite a bit to. Another game that we've been playing is approximate Markov chain Monte Carlo, which it's quite strange until recently. What everyone has been doing religiously in the community that works on these problems is to define a Markov chain Monte Carlo algorithm that has a Markov transition kernel converging to exactly this posterior distribution, the exact posterior distribution. And so you want to have no bias. And so that seems to be ridiculous. And so by putting in a little bit of bias, like have an approximate transition kernel instead of an exact transition kernel, you can actually maybe get orders of magnitude speed up. And then the question is, can we characterize theoretically that it still converges, and it maybe still converges to within a small neighborhood of the target posterior distribution? And I'm really quite excited about that. We have a paper under revision that handles the statistics. This really brilliant PhD student of mine, who's now a Stein Fellow at Stanford, was working on this. He defined a new concept called comp minimax, and so you could say, well, I have a broad class of MCMC algorithms. I have some approximation error epsilon in the transition kernel. As I make epsilon larger, I can evaluate the transition kernel faster. And there's many settings like this I'll describe in more detail given time. And so if that's true, then if you have a particular computational budget, say in 10 minutes I want to get a lowest possible Monte Carlo error in some estimated posterior summary of some functional f of theta, then I can define an optimal algorithm under this in the worst case scenario under the comp minimax framework. And so it's pretty cool. A third thing I'd like to talk about given time is data augmentation algorithms, particularly for kind of discrete and imbalanced data. Discrete data, imbalanced. Because often what people do in solving this problem, it might be hard to directly define a Markov chain Monte Carlo algorithm for this posterior. And so sometimes what people do is they introduce latent data z, okay? And so that you make the problem kind of worse by you define some posterior phi of theta given y, theta and z given y. And that's a bigger space because now you have the joint posterior of the parameters and some latent data. But it might be that in introducing the latent data, you've made all the operations a lot easier. Now it's almost like an EM algorithm type thing, but for sampling. So that's extremely common to use data augmentation algorithms. They're used just all the time in Bayesian inference, okay? And so, we've been studying recently what happens with these data augmentation algorithms in terms of their computational efficiency theoretically if you have really big data problems, okay? And we have some quite strong results on that. But I'll just kind of click off these three topics, and please interrupt me as we go, okay? So embarrassingly parallel MCMC. So what we wanted to start out with is, okay, well, really what I'm most interested in is so-called like big P problems. But let's start out with like big N problems. And so let's say the likelihood of y given theta can be written as some sort of product from I equals 1 to n of L of, you could say, yi given theta. Okay, and so so this is reasonably broad, but you could think of this as the sample. This is the sample size. And so we have some likelihood that takes a product form, and so logistic regression or generalized linear model or anything like that would fall in this form. But we can also allow the thetas to include latent variables or random effects, and so that we have some sort of conditional independence here. And so it's actually pretty broad. Yeah.
I was just informed. The board slides over to reveal more board.
Okay, that's cool. Yeah, look at that. Wow.
In case you want to fill up more boards.
Yeah, but now it's on the wrong end. It's, no, I'm kidding.
It's up to you.
Okay, thank you. That wasn't a very deep question, though, I know. Okay, so if we have this type of setting, which is quite broad, what happens is as the sample size increases, it becomes harder and harder to do MCMC efficiently because often the per iteration computational cost goes up in the sample size. Okay, and so what can we do? Well, we would like to be able to maybe put the data on different machines. And so if we could define, say, K is the number of machines or processors, can we do some sort of, well, let's say Y of J is this sort of shard or chunk of data on machine J. Okay? And so, well, we would like to just throw the data in advance on different machines because the data are enormous, and maybe run MCMC in parallel on each machine and then combine the results really efficiently somehow. Okay? That would be embarrassingly parallel MCMC. And so we throw the data on different machines. We don't want to have a lot of communication costs because that's going to drag things down horribly. There's been some work in using GPUs for MCMC, but it hasn't really been that successful because of communication costs. And so what can we do? Well, we could imagine defining some subset posteriors, pi of theta given y of j. This is the jth subset posterior distribution. Okay. And so that we could define this guy as pi of theta, and then L of y of j given theta. And then we'll have our normalizing constant. But what we're going to do is we're going to raise this guy to the power k. Okay, so we're going to, just for simplicity, we won't have to do this. We'll put equal sized chunks of the data on different machines. And then we're going to define a kind of noisy approximation to the full data posterior using subsets. And how we're going to do that, we'll take the prior distribution, and then we'll take the likelihood, and then we'll just replicate the data on that J subset k times, and so that the effective sample size is now the whole data sample size. Okay? And so what we do, if we plotted what the subset posteriors look like, the true posterior might be, that's kind of computationally intractable, might look like this. Okay, well, the subset posteriors, if we didn't do this raised to the power k, they would be like flatter. Okay, they might look like that or something. So if we raise to the power k, then we're going to have subset posteriors that look like this. And so it's a type of stochastic approximation, which has been obviously enormously popular in machine learning and other contexts. But here we're doing a type of stochastic approximation of the full posterior distribution. And so we have a bunch of posterior distributions that are noisy estimates of the target right here. So we're interested in this guy. We can't get him, and so because it's computationally intractable. And so instead we get some estimates of a bunch of subset posteriors that provide normal noisy approximations to the true joint posterior. And then maybe we can take some appropriate notion of mean or median of those distributions, and that'll give us a good approximation of the true posterior distribution. Okay? And you could kind of think of this in some sort of general space, call this M or something, and then each point you could say would be a probability measure corresponding to a different one of these subset posteriors. They're kind of noisy approximations to the true posterior. And so this in some sort of Banach space or something, each of these points would be a posterior distribution or posterior probability measure. And we would like to get an estimate of this guy, which corresponds to, maybe here, maybe the truth is right here. And we get pretty close by taking some sort of mean, appropriate notion of mean in this space of probability measures, okay? And if we could do that efficiently, we could imagine running MCMC in parallel on each machine and then doing something really efficient to get this estimated mean and then do inferences based on that, okay? And what we were able to kind of work that out quite beautifully, I think, and we have a kind of series of methods. The first one is what we call WASP, for Wasserstein barycenter of subset posteriors. And so you can call define a Wasserstein barycenter as some notion of mean in this set of probability measures. And so, if we have this central point, we need to define some sort of distance, between probability measures. And a natural distance is a Wasserstein distance, okay? And if you use a Wasserstein 2 distance, and then you find the point that minimizes the sum of those Wasserstein 2 distances from a central point to all of these different points in the space, then that's known as the Wasserstein barycenter, okay? So in general, the Wasserstein, and there's some wonderful work by Couturi and Arnaud Doucet and other people on efficiently calculating Wasserstein barycenters. And we were able to build on that actually, and so that if you use the sample so that each one of these guys is atomic, which you would have if you ran MCMC for each of these subset posteriors, you would get something that looks like what? It looks like 1 over the number of MCMC iterations of t equals 1 to t. And you could put weights on if you and allow some sort of weighted sampler or sequential Monte Carlo or something, but have some sort of theta of t kind of deal. And so all of the subset posterior, this would be the jth one, say. Let's just say j. Okay, and so this would be our noisy Monte Carlo estimate to the j subset posterior. If each of these points take this form, then we can actually solve for the Wasserstein barycenter using a sparse linear program. And so it's very fast. And so all we have to do, we throw the data on different machines. We run MCMC in parallel on each machine with the likelihood raised to a power, which you can easily do, for example, in Stan, which is an automated thing for doing MCMC. And then you just take the results, and then you just throw back the samples to some central machine and solve the sparse linear program very quickly. And then you get an approximation to the full data posterior pi of hat of theta given y, which is also going to have this kind of atomic form, just say. Pi t of delta of theta t. So it's going to have this form. So we sample in parallel, we feed back to the central processor, and we get this atomic approximation of the full data posterior. Based on that, we can do all the things you usually do in MCMC to get point and interval estimates for any functional of the parameters that we care about. Okay. Yeah.
So does this enjoy any theoretical guarantees, say if the data are randomly spread on these machines relative to the exact posterior?
Yes, we have quite strong theory guarantees on it from a variety of perspectives. And so we can say that this guy is actually, for one, we can say that there's going to be some, from a frequentist perspective, we can study the properties of this guy. And so we could, the best parameter, in your parametric class of models, say, if you have a parametric class of models, there might be some theta naught, which gives you the parametric model in that class that's closest in the Kullback-Leibler divergence to the true data generating model. The true posterior is going to be concentrating around that point. So this guy is also going to be concentrating around that point at the same rate. And we can also get a handle on the distance between the two and get nice bounds on that depend on both the
bounds between this and the post-exact.
Between this and the exact posterior and Wasserstein distance, and that's going to depend on k and on m. And our initial result was not strong enough because I don't want m. M is the subset sample size. what I'd really like is that the subset sample sizes, the amount of data I put on each machine, I don't want that to blow up because that would be cheating. Because we want to blow up the number of machines, that's the appropriate asymptotics. And so we were able to get a quite good result in that respect, in that we can grow the amount of data on each machine very slowly, so kind of like a log rate, and then blow up the number of machines and still get the distance between the approximation and the true posterior vanishing, okay, and a quite broad class of models. And so we weren't quite satisfied with this because it's still kind of complicated. And so we actually came up with something that I'm super excited about, which was just a couple weeks ago accepted at Biometrika, which is as follows. And so what do we actually do? This is some high dimensional thing. If you're doing Bayesian inference in practice, we have these parameters. Well, we're really interested in functionals like f of j of theta of the parameters. Like, these might be a bunch of coefficients in a logistic regression model, but we want to get the predictive probability of a 1. The patient has a disease given their predictors. Instead, that would be like a one-dimensional functional. Okay, so we might be interested in a bunch of one-dimensional functionals. Almost always, you're doing inferences on the posterior for one-dimensional functionals. So if that's true, there's an amazing result. And so the amazing result is that the Wasserstein barycenter in the one-dimensional case can be calculated analytically, and so that we can actually do something really cool in our algorithm. And so if we're interested in, like, this is a one-dimensional posterior. If we're interested in any one-dimensional posterior, our algorithm only has to do the following. We run MCMC in parallel for each subset posterior. Okay? We calculate a percentile of interest for any functional, one-dimensional function we care about on each machine. We feed that back to the central machine and we average. That's all we do, okay? And then we can just build up at each percentile, we can build up this very theoretically, very, very strong result, theoretically approximation to the true posterior using this really trivial algorithm that we could do in like Stan or something. On each machine, we run for our chunk of data, MCMC with the likelihood raised to that power. For any percentile of any one-dimensional posterior of interest, and we can actually extend it to multivariate as well. We calculate that percentile. We just feed back those percentiles to the central machine, and we average them. Okay, and we get very strong asymptotic and small sample results on concentration bounds on how close those are. Yeah. Are there any questions about that? We're pretty excited about that because it's a very broad class of algorithms for scaling up MCMC, and it has quite strong theoretical guarantees, unlike all of Dave's stuff. Yeah.
It sure feels like variational inference, right? Minimizing the distance.
Yeah, it does. Yeah. I'll give it to you.
I think you're on the same team.
No questions. Okay. Okay. So that's point 1 in the talk, and so I'm running out of time. So that's EP MCMC, what we were kind of playing with that. And we're also working on ways where you can divide up the variables. We have an approach that we have close to submission where you have like millions of variables, and you can actually subset the variables and then do computation separately for those and get good posterior approximations. But that's more, it's not a general result like this. Okay, so the second topic that I was going to go over was MCMC. Okay, just briefly. Okay, so this is approximate Markov chain Monte Carlo. And so usually what's the game? So we have some target posterior pi of theta given y, and we define some sort of transition kernel, call it kappa, okay? And so that transition kernel is giving us samples theta t. So we have a sample theta t minus 1. We apply this transition kernel. We get a sample theta t plus 1. And then we have to have that transition kernel obey the proper Markov chain Monte Carlo rules, or it's not going to converge to the right thing. And there's all sorts of elaborate algorithms trying to design Ks that are really good, that can solve general problems and converge quickly, et cetera, et cetera. Yeah. Ryan's done beautiful things in that area, for example. Okay, so what occurred to us is that, well, what if we instead relaxed this and made it like K of epsilon? Okay, and so now we have a transition kernel. This is the transition kernel for some sort of exact Markov chain Monte Carlo algorithm. This is a transition kernel for an approximate Markov chain Monte Carlo algorithm. Maybe this transition kernel is way faster to approximate. What would be one example? One common example, I think Emily's worked on this, for example, would be to use some sort of stochastic approximation. Okay, so this transition kernel, if we apply religious Markov chain Monte Carlo, and we use the full data likelihood, that might be too slow. And so we might be able to approximate our transition kernel by taking a subset of the data and then using some sort of a stochastic approximation. And that'll give you an approximation of the transition kernel based on the subset. So this might be a stochastic gradient based, it might be just based on the subset in other contexts. Okay? And then you can control epsilon based on the size of the subset. So if the subset was really small, epsilon's going to be really big. Okay? So what do we do? Well, we'd like to know how the hell do these behave? And so we have two assumptions. Assumption one, the exact MCMC mixes well. That's the dopey version of assumption one. It mixes well. And so we have some chain that we don't have to ever run that we're going to approximate that mixes well. So it's going to satisfy a Dublin condition, which I won't get into the technical details, but it mixes well. But we don't have to ever have to run it. And assumption two is that K epsilon is close to K, okay? And total variation distance, uniformly. Okay, so these are the two assumptions. And so based on these two assumptions, we can show that, well, it's going, the Markov chain Monte Carlo algorithm based on this guy is going to converge to pi of epsilon theta y, okay? And that guy's close to pi of theta given y. But more than that, we were interested in, well, what are we actually using Markov chain Monte Carlo for? We're using it to generate these samples, theta of t, and then based on those samples, we're calculating, again, these functionals of the parameters. So we want to calculate some sort of posterior summaries for these functionals. And so what do we want? Well, if we're running this thing t times, we want the Monte Carlo error in some posterior summary for some functional of interest to be small. And we want it to be decreasing in clock time as fast as possible. And so if we run our MCMC algorithm for 5 minutes, we would like say the Monte Carlo error in the posterior mean for one of the parameters that we care about a lot to be as small as possible, okay? What's controlling the Monte Carlo error? There's two parts. The first part is the asymptotic bias. The error, our error in this guy based on our approximate Markov chain Monte Carlo is depending on the asymptotic bias. Asymptotic bias is going to be increasing with epsilon. The second part is just a sort of pure Monte Carlo error. So that's going to be decreasing at the usual rate in the number of samples, okay? So the game here is, as epsilon increases, we would like to increase the number of samples we can draw per unit clock time by S of epsilon, okay? And so maybe as epsilon gets bigger, maybe S of epsilon will be 10 or 100 or 1,000. And so we can calculate, we can generate 1,000 times as many samples in the same clock time. But those samples are giving us some more asymptotic bias. And so there's going to be some sort of optimal point that depends on the particular computational budget you have. And for a particular computational budget, there's going to be an optimal, and the loss function for what you care about. For those two things, there's going to be an optimal choice of epsilon, okay? And we were able to study several classes of algorithms that people use all the time and prove that these assumptions hold and get actually practical insight into their use. And it was pretty interesting, actually. And so what did we look at? We looked at logistic regression, with, I'll call it stochastic approximation. It's like a mini batch-based logistic regression. And so people do these things all the time. And so, oh, I have like a 10 million sample size, and so I can't run sampling for logistic regression, so I use subsamples, okay? And so the subset sample size, as that becomes smaller, epsilon becomes bigger. And we can get a perfect handle on that, okay? We can show that these two assumptions hold, and something interesting happens. Okay, well, I want to do logistic regression. I have a really big sample size. And what's optimal? Well, what we found is that this doesn't work very well because the epsilon is pretty damn big unless the subset sample size is huge. And if the subset sample size is huge, we don't get much computational speed up. And so maybe in other contexts, these mini batch-based methods work well, but in ours, you could kind of show that it doesn't work well at all. And so that was kind of a surprising result that the theory kind of exposed. And then you could look at it practically and say, yeah, that's true. Actually, these mini batch things don't work very well. The other thing that we looked at sort of adaptive Gaussian approximations. Okay, so you can imagine I'm running some sort of MCMC algorithm. If I have a lot of information about certain of my parameters, maybe I'll just use some Gaussian approximation, and I could do that cleverly. Maybe I can avoid, maybe I'm running a mixture model, and I have to like sample all of these mixture component indices, and there's like a million of them. Well, if I can look at where that stuff comes into the computation, I can instead put in a little Gaussian approximation and avoid sampling all those things. And so that actually works quite well. Another thing we looked at was Gaussian process models. So for GP models, theta is actually a function, a regression function or something like that. Okay. And so this was quite interesting as well because there's already a lot of AMCMC methods that are ad hoc that people use where you would, say, substitute in a low rank approximation when you're doing MCMC algorithms or something to reduce the order n-cube bottleneck that you have in a Gaussian process model. But our conjecture is that most of these algorithms actually don't satisfy the assumptions, and most of the algorithms will, if they converge at all, converge to something that's super far from the target posterior. Maybe that's fine as long as it works well. But we could find one class of algorithms that actually works well and satisfies the conditions. And in this case, you could get, like for epsilon really small, you could get a huge computational improvement. And so this was a big win. Unlike the stochastic approximations, the GP-based model approximations with, say, low-rank approximations, you could have a very small epsilon and still get a really big computational advantage. Okay, so that was kind of cool that you could get some tractability theoretically in these. Okay, so in my remaining time, 5 minutes, I'll go to the third topic. And so the first is the CP MCMC. The second is approximate Markov chain Monte Carlo. The third is most recent work that we've been doing on data augmentation algorithms. Okay. So DA MCMC. So people use this constantly. And so you have you care about pi of theta given y, but you do sampling for pi of theta and z given y. Throwing in the z makes things a lot easier. Once you throw in z, maybe the conditional for theta given z and y is now just Gaussian or something like that. So there's some very popular algorithms. The one is sometimes called Albert and Shib. It's for probit models. So if you have like any sort of categorical data model that's based on a probit link function, this has been used probably hundreds of thousands of times. Not cited that much, but it's used constantly. There's now a quite beautiful algorithm called, for logistic regression called Polya gamma data augmentation. Okay, and that works really well as well. We throw in some latent z's, and now everything's Gaussian again, and we can just apply wonderful things, and it's all beautiful. And both of these algorithms have been shown to have really nice mixing properties, like they're geometrically ergodic and things like that. But if n is huge, what happens? Particularly if the data are imbalanced. okay? And so, which often happens, say, well, if the sample size is really big, how we started working on this was actually a computational advertising setting where we wanted to look at a flow of users between websites. And N was enormous, but it's sort of rare to go to the client website from a particular starting website. So the data are really imbalanced. So the N is huge, but most of things are zeros. Mostly things, most of the data is zero, but N might be hundreds of millions, but most of the data are zeros. So if that's true, what we could show is that we have a theoretical paper showing that the mixing rate of these algorithms as the sample size gets big for badly imbalanced data goes to 0. And so you could actually bound the spectral gap of the Markov chain so that the mixing rate goes to the 0 and the square root of the sample size are faster, which is an amazingly bad result for these models. And we were motivated by, we were actually trying to solve a computational problem in that computational advertising application, and we could solve this time per iteration, but the mixing rate became horrendous. And so even in a very simple problem, if you look at the kind of lag, the autocorrelation plot, and so you're looking at the correlation between theta of t and theta t plus delta, it can be like this, and this is like 100. And so you have to run your MCMC algorithm for like 100 billion iterations to get a decent number of samples, okay? And so that was disturbing for these data augmentation algorithms, because we often have really big imbalanced data. And we have a bunch of ecology collaborations like this, and we were having a hell of a time getting any sort of MCMC algorithm to work. And we tried to convince them to use variational, but they just thought they wouldn't work at all. So anyway, the amount of time, but the thing we found is that you could actually calibrate. There was a deep thing going on here, theoretically, that we studied it theoretically, and we could figure out what was going on. And so the reason that these algorithms fail, or when they fail, is when there's a mismatch. Okay, so what are you doing in your MCMC algorithm? You're going to be updating the thetas maybe in different blocks, given the z's, and then the z's given the thetas, and you're going to kind of iterate through. But what if you think about what's happening as n increases? You know, your posterior distribution, the pi of theta given y, even if it's one dimensional, it's going to be increasing, getting narrower and narrower. Okay? But what if the rate of concentration of this posterior is not the same as the rate of concentration of pi of theta given z and y? What if throwing in augmenting the data, the conditional posterior converges faster? That actually often happens. And so if these concentration rates of this guy and this guy are mismatched, then as the sample size gets bigger and bigger, you're going to get worse and worse mixing. And the algorithms are going to do disastrously. And so this would be true just broadly. We studied for these algorithms and some other algorithms, but this is true broadly. If you have this mismatch, you're screwed, okay? And so what we did is we could actually calibrate the data augmentation algorithm to adjust for the mismatch. And if we calibrated, then the autocorrelation plot went from that to like that, just by applying a quite simple calibration to the data augmentation algorithm.
Calibrate, you mean arrange matters so that the conditional posterior concentrates at the same rate as the unconditional posterior?
Yes, yes.
But that's changing the posterior, or you're changing the way that you're...
Yeah, so it's in some specialized settings, you could not change the posterior, but in general, you're going to change the posterior slightly. You could use that and just as an approximate posterior, sort of like a variational approximation as approximate posterior, or you could use that as candidates in importance weighted, or use it in Metropolis Hastings. Okay, and so all of those things work reasonably well. Yeah.
Dave,
Yeah.
does this come up in like HMC and Swinson-Long and other algorithms that are also sort of data augmentation, but for the algorithm itself? Or is this focused on where you have sort of one auxiliary variable per data?
No, it'll come up in those other cases as well, I think. And so it's really interesting to study. I mean, we were just starting in this case, and then we're like, well, this is going to happen in general, yeah, if you have that mismatch. And so it would be really cool to kind of apply to these other settings as well. Okay, I'm done.
One more question?
It's just a quick question about MCMC.
Yeah.
So here, okay, so the transition kernel is, it's a hassle to simulate exactly. So you have this approximate version. So the K of epsilon, is that the expected transition kernel then?
No, that's your approximate transition kernel. And so so you have your original transition kernel K, and then if you have error epsilon approximation, then you call that K of epsilon. And so you could actually call it technically it's like a class of transition kernels that are within that kind of ball. But
So one of the ways you were describing or constructing this was the subsample of the data, right?
yes.
And so there, do you think would be enough to just talk about the expected kernel you get?
Oh, that's a good question. Yeah. Because you don't have like you're talking. There's might not exact correspondence between the subset sample size and epsilon. Yeah, you do the expected, or we were looking at kind of like a comp minimax framework where we can look at the worst case transition kernel within the ball kind of thing.
Yeah, the other thing about that is that what matters, is it the actual discrepancy between K and K epsilon or between the stationary distributions that they use?
Yeah, I mean, so we had, what would be interesting, we had quite strong, those assumptions were reasonably strong, and so that you could match those two things together. And so because K epsilon was close to K, and under this other condition, then you could show that the stationary distributions are close.